welcome to the fifth lecture of the course on high performance computing. We are currently trying to understand a little bit more about what happens inside the processor, because this will be important to get an understanding of what happens when our programs execute, and to understand about the individual instructions that our program might get compiled into. We understood a little bit about what the different operations were in the previous lecture, and also about the addressing modes, the mechanisms through which the instructions specify where the operands are coming from. So let me just move forward to what we were looking at last time. The operands to an instruction are described as either the source or destination, depending on whether they provide input values or are the destination where the result is to go. And the addressing modes are the mechanisms, basically the encoding mechanism through which the location of the operand is indicated inside the instruction. So since the instruction operands can come either from registers or from main memory, there are special addressing modes for the operands coming from registers, such as register direct, as well as the immediate addressing mode, all of which we saw in the previous lecture. Now, we were in the process of looking at addressing modes for operands coming from memory, and we saw the register indirect addressing mode, in which the address of the operand in memory is placed into a register, and then the identity of that register is included in the instruction. Ultimately, the operand is coming from memory. Then we looked at the base displacement addressing mode, which uses a computation, a very small computation, in order to calculate the address of the operand, it adds the contents of a register to a displacement, which is mentioned inside the instruction. And then the absolute addressing mode, where the address of the operand in memory is contained inside the instruction directly. So there are in fact more addressing modes than these. It may come as a bit of a surprise, because all of these are just mechanisms to specify where an operand is present in memory. But as I had sort of alluded to last time, for different kinds of C or high level language programming constructs, or for different kinds of instructions, one or the other of these addressing mechanisms may be most appropriate, which is why people may use them in designing an instruction set. These are not decisions that a programmer makes. These are decisions about these addressing modes are made by the person designing a computer, the computer architect. So moving right along, let me just mention that one of the somewhat important addressing modes is the indexed addressing mode. And the indexed addressing mode uses a slightly more complicated calculation to calculate the address of the operand in memory than the base displacement addressing mode does, because the address of the operand is specified through two registers, and the contents of these two registers, when added, gives you the address of the operand in memory. It turns out that this addressing mode is very useful for programs, for example, which have references to arrays. For example, if I have a C program in which there is a two-dimensional array called A, you know that a reference to A will require two subscripts, the row subscript and the column subscript. And ultimately, the array is going to be stored in memory. And our view of memory is linear. There's a memory addresses which are unsigned integers. So obviously, this array reference A of ij has to be converted into an address using the starting address of the array and the actual values of I and j, which will require some computation. And the indexed addressing mode is very useful for this kind of a reference inside a program, which is why we often find it in instruction sets. Right, so these are the four main kinds of addressing modes for operands which are in memory, but there are others. So I will just mention some of them in passing. Okay, now one class of addressing mode which one may find in slightly more complicated computers, such as the RISC computers, is an addressing mode where there could be side effects of the operation of computing the address of the operand. For example, there could be addressing modes where automatically the contents of the register which is used in calculating the address of the operand could get decremented or incremented, either before or after, hence the pre or post, before or after the calculation of the address is done. And as you can see, this is a significantly more complicated addressing mode than any of the others that we have seen. And that's why I suggested that this might be the kind of addressing mode you would find in a CISC architecture, maybe not in a RISC architecture. Of slight more interest to us is the addressing mode called PC relative. And we have seen that PC stands for the program counter, which is one of the special purpose registers in the CPU. The program counter at any given point in time contains the address of the instruction which is currently being executed. Therefore, to say that there's an addressing mode which is PC relative means that the address of the operand in memory is being specified as an offset from the address of the instruction which is using that operand. And this may be convenient for certain kinds of instructions. Right? So, the idea is that the operand address is specified as a displacement from the PC value. In other words, from the address of the instruction itself, the instruction which is going to use this operand in its computation. So, there are a wide range of different kinds of addressing modes, and as I had alluded to last time, they go by these names, and we will expect, if we look at an instruction set architecture manual, we would find the addressing modes described using these terms. So much for addressing modes. Now that we have an idea about what the operations, the instructions we can expect inside an instruction set, and we have some idea about how the operands to those instructions might be specified using addressing modes, it's time for us to look at a specific instruction set. And the example which I have chosen to go through is a simple RISC instruction set, reduced instruction set computer. The properties of RISC processors are that each instruction does a single, somewhat simple operation, as opposed to the CISC instruction sets, where an individual instruction might do a fairly complicated operation. Right? So, we will be using the instruction set architecture that I am going to discuss for the rest of this lecture for all of the examples in the rest of this course. And therefore, I will be going through it in a little bit of detail, because we will end up possibly writing code segments or understanding code segments written in this instruction set to understand the other concepts of computer systems. Right? So, the reason that we are doing this is that I will have to use examples in the rest of this course. Now, the particular RISC instruction set which I am going to use as example is known as the MIPS1 instruction set. Every instruction set will have to have a name so that we can distinguish between the different instruction sets. And the MIPS1 instruction set was one of the first RISC instruction sets. MIPS was the name of a company, and is still the name of a company today, a new incarnation of the same related company. And I am referring here to the first instruction set designed by that company. Subsequently, they have updated versions, the MIPS2, the MIPS3, etc. instruction sets. We'll start with the first and simplest, which will be adequate for our purpose. Okay, now in order to give you an idea about the instructions in this instruction set, as I said, I'll have to give you some idea about what registers are available inside processors which implement this instruction set. So that's our first task. And to be brief, the MIPS1 instruction set assumes that there are 32-bit general purpose registers, which we will refer to as R0 through R31. Right? So there are 32 of them, hence the names are R0 through R31. Remember that the general purpose registers are fast, small pieces of memory inside the CPU, which are available for any for any purpose that the programmer or the compiler wants to use. Typically, they are used for storing frequently used pieces of data. Now, in the MIPS1 instruction set, there are a few peculiarities which we must be aware of. So let me just mention them. The first and somewhat important peculiarity is that even though there are 32 general purpose registers, R0 through R31, not all of them are actually available to the programmer to do whatever he or she wants. For example, R0, as we see in this next point, is hardwired to 0. And what I mean by hardwired to 0 is that R0 always contains the value 0. There's no way to change that. If you wrote a program in the MIPS1 language and tried to change the value of R0, the instruction would not be illegal, but it would not have any effect on R0. R0 would ultimately still contain the value 0. And this is a very curious design decision. Why do the designers of the MIPS1 instruction set decide to have a register which always contains 0? Now, when we start writing code segments, you'll realize that this is actually a very useful thing to have. Frequently, when you are writing a program, there will be a situation where you want to compare something with 0. For example, I may want to check if the value of the variable x is equal to 0. 0 is therefore a very frequently used constant by programs, and having 0 readily available in a register makes the speed of operation on 0 all the faster. Otherwise, my program would have to have 0 as a variable stored in a variable somewhere, or have 0 as a constant somewhere in memory in order to do that comparison. So this is not that uncommon in RISC instruction sets today, to have registers which contain fixed constants and cannot be changed in value. In the case of the MIPS1, R0 is one such register. So we can use R0 as a source of the value 0, and we cannot change the value of R0. R31, the other end of the register spectrum, also has a peculiarity, and that is that R31 is implicitly used by some instructions. And what I mean by implicitly is that if I looked at the instruction, particular instruction, then I would not find R31 mentioned as an operand inside the instruction. So it is not explicitly used as an operand of the instruction, but it is implicitly used, in other words, without being stated inside the instruction. And therefore, one has to be a little bit careful as a programmer or as a compiler writer in using R31, because I may think that I can use R31 as the place to temporarily store the value of my variable x from memory, and then I may cause certain instructions to be executed. And some of those instructions might be instructions that implicitly use R31 as a destination, in which case the value that I had stored in R31 will no longer be available. So as programmers, this is an important issue. We must be aware that R31 may not be a good register to use for storing values temporarily unless we know exactly what the instructions, the subsequent instructions, do. If they are instructions that implicitly use R31, we must take that into account. Now, other than these peculiarities with R0 and R31, the other 30 registers are actually freely available for the programmer or compiler to do whatever he or she wants with. So in other words, R1 through R30 are real general purpose registers. Now, there is one other point which we must be aware of about the MIPS1 registers before going ahead, and that is, before going ahead, let me give you an example of one of the instructions that implicitly uses R31 as an operand, and that is the instruction JALR, and I am giving you here an example of using JALR with the operand R3. So you notice that R31 is not an explicit operand of this instruction, but this instruction does modify R31. R31 is a destination of this instruction, and we will see what JALR is a little bit later. Now, there is one other issue regarding general purpose registers in the MIPS1 instruction set that we must be aware of, and that is that in addition to the 32 general purpose registers R0 through R31, there are in fact 2 more general purpose registers that are known as high and low, HI and LO, and they too are 32-bit registers. Now, the very fact that they are not referred to using a continuation of the name sequence that was used for the other 32, in other words, these are not called R32 and R33, but they are called by names high and low, means that they are actually used for certain specific purposes, though they will be available to the programmer in general as well. So the specific purpose that high and low are used for relates to the multiply and divide instructions. All the MIPS1 multiply and divide instructions implicitly use high and low, and we will see this when we talk about the multiply and divide instructions. So just to sum up, an example of multiply would be multiply R1 R2. So it has 2 operands R1 and R2, and it implicitly uses high and low as well. So in brief then, the important general purpose registers of the MIPS1 are the 32 general purpose registers R0 through R31, of which R0 is hardwired to 0 and cannot be modified. R31 is implicitly used by some instructions. In addition, there are the high and low registers, which are implicitly used by the multiply and divide instructions. Now, I do need to tell you what addressing modes are used. Before we look at the instructions, we must be aware of all these things. So the use of addressing modes by the MIPS instruction set is somewhat simple. The immediate and register direct addressing modes are used by the arithmetic and logical instructions. We had seen that there are 4 categories of instructions to expect: the arithmetic and logical instructions, the data transfer instructions, the control transfer instructions, and the special instructions. So we are learning now that all of the arithmetic and logical instructions use the immediate and register direct addressing modes. You will recall that the immediate and register direct addressing modes from the previous lecture, we learned that these are the 2 addressing modes which take their operands out of registers. The register direct addressing mode takes operands out of the general purpose registers, and the immediate addressing mode takes its operands out of the instruction register, because the operand is available inside the instruction. So this is going to mean that all of the arithmetic and logical instructions will be able to execute without having to access operands from memory, and therefore they will be able to execute much faster than would have been the case if they had memory operands. So once again, this looks like a good design decision by the architects. Arithmetic and logic will be as fast as possible. Now, the absolute addressing mode is used, but only by jump instructions. You recall that I am using the word jump to refer to those control transfer instructions which are unconditional, right, in which there is no condition. So, sort of related to the go-to statement of the C program. Right? And the absolute addressing mode is not used anywhere else. Next, the base displacement addressing mode is used by load and store instructions. And you will recall that the base displacement addressing mode is the one where the operand is coming out of memory, but the address of the operand is calculated as the sum of a base register, the contents of a base register, and a displacement, in other words a small signed value which is contained inside the instruction. So after adding these 2 values, one gets the address of the operand in memory, and this is used only for loads and stores. Remember that a load instruction is an instruction which can be used to copy a value from memory into a register. And the store instruction is an instruction which can be used to do the reverse. In other words, to copy the value from a register into a memory location. So these are the 2 kinds of MIPS1, as we are going to see, the 2 kinds of MIPS1 instructions which deal with operands out of main memory. And both of them use the base displacement addressing mode. Finally, the PC relative displacement, which I spoke about a few minutes ago, is also used in the MIPS1 instruction set. In particular, it is used by conditional branches. And I had indicated in the previous lecture that I will use the term conditional branch or just branch to refer to a control transfer instruction which has a condition. So if the condition is true, then the branch control transfer takes place. And for such MIPS1 instructions, the PC relative addressing mode is used, where the address of the operand, in other words, the target of the branch, is indicated as a displacement from the PC value, or by which we understand that means a displacement from the address of the branch instruction itself. Now these are the only addressing modes used in the MIPS1 instruction set. There is no index addressing mode. None of the other addressing modes that I talked about are used. So things are a little bit simpler than they could have been, and this will allow us to quickly understand the examples that I see, that we are going to see. And if we had used the MIPS2, MIPS3 or MIPS4, we would have found more sophisticated addressing modes used. But now, since you understand what the addressing modes mean, once you have understood the MIPS1 instruction set, you will quickly be able to understand MIPS2, MIPS3, MIPS4 programs without much difficulty. Okay, so moving right along, I will start by making a few general comments on the MIPS1 instruction set architecture before we actually look at the specific instructions. Now the first comment the first thing which we should be aware of is that in the MIPS1 instruction set, all of the instructions, just like all of the registers, are 32 bits in size. So every single instruction is 32 bits in size. If you have looked at, or you may be aware of RISC instruction sets, there are many RISC instruction sets where, because there are some instructions which are very complicated and other instructions which are very simple, different instructions might be of different sizes. You might have some instructions which are 8 bits in size, other instructions which are 32 bits in size, and so on. So that complexity is eliminated in the MIPS1 instruction set because all instructions are exactly the same size, 32 bits. Another characteristic of the MIPS1 instruction set is that while it is, as I had mentioned, a RISC instruction set, you may also see it described as a load-store instruction set or a load-store architecture. And it is given this name because the only instructions in this instruction set that take operands out of memory are the load and store instructions. All of the other instructions take operands out of registers, and this is going to help to make the instruction execute faster. There is no need for those instructions to wait for an operand to come out of main memory at 2 orders of magnitude slower speed than the processor, as we had seen a few lectures ago. So the MIPS1 instruction set is a RISC load store instruction set. Now, some of the terminology that is used in the MIPS1 manuals will be of importance to us. So let me just outline this. Now, in the MIPS1 instruction set, the word WORD or word is used to refer to a 32-bit quantity. In other words, the word size of the MIPS1 instruction set is 32 bits. However, certain data values might be 16 bits in size, and other data values, as we have seen, might only be 8 bits in size. For this reason, they have a term for a 16-bit quantity, half word, and they have a term for the 8-bit quantity, which is byte, as you would have expected. So the 3 terms in the MIPS1 instruction set relating to the size of something are word, half word, and byte, corresponding to 32 bits, 16 bits, and 8 bits. And in the case of subsequent instruction sets in this series, such as the MIPS3, MIPS4 instruction sets, if they had data values which were larger than 32 bits, they would have a word, a term to correspond to that. But that's not a problem for us in the MIPS1 instruction set. Now, another important thing to note in the case of the MIPS1 instruction set is that we saw that the base displacement addressing mode is going to be used to specify the operands of load and store instructions. And we also saw that the arithmetic and logical instructions can have immediate operands. In addition, that the load store instructions have a displacement. Now, these values, the displacements and the immediate values, are going to be constants that are present inside the instruction. And therefore, we need to know how big those constants can be. They're all going to be signed integer constants. It turns out that they are all of size 16 bits. And again, this may not be too much of a surprise because I've mentioned earlier that all the instructions are of size 32 bits. Therefore, it was clearly impossible to have a constant inside an instruction which is of size 32 bits. That would have taken up the entire instruction. And we now learned that the size of the constants inside the instructions is that they could be 16, they are signed 16-bit quantities. Okay, now with this few general comments on the MIPS1 instruction set, we can actually go ahead and look at the MIPS1 instructions one by one. Now, I'm going to start by looking at the data transfer instructions. So, in the tables that I'm using to describe the instructions, I'm describing a lot of instructions, the whole category of data transfer instructions on this one slide. And you'll notice that I have one column where I've labeled it as mnemonic. And in this column, I've included the names of a name which could be used to describe that instruction. Obviously, since we're talking about machine instructions, I should be showing you the bit pattern corresponding to that instruction. But if I showed you the bit patterns, it would be difficult for us to understand programs. So I'm going to raise the level of discussion a little bit by abbreviating the bit pattern into a mnemonic, an easy to use, easy to remember a word as a replacement. Next, I'm showing you an example of using an instruction of that category and then a description of what the meaning of that instruction is. So there are 3 categories of instructions in this table. There are the load instructions, there are the store instructions, and then at the bottom I have something called the move instructions. And remember that the load instructions are used to load values or to load a value from main memory into a general purpose register. Store instructions are used to store a value from a general purpose register into main memory, and move instruction is used for some other form of data movement. Now, before actually going into the instructions one by one, I am going to put up some information which is generally applicable to understand the terminology which is used in these mnemonics. So basically, whenever there is an instruction that starts with the letter L in these tables, it is a load instruction. Whenever there is an instruction that starts with the letter S, it is a store instruction. An instruction that starts with the letter M is a move instruction. Whenever in this table we see a B, it stands for movement of a byte. Whenever we see an H, it stands for movement of a half word or a 16-bit piece of data. Whenever we see a W, it stands for movement of a 32-bit value. And in addition to this, some of the other terminology which is present in this table, you will notice in some places there is a U, for example, over here. And in general, U stands for unsigned. In some cases, there is an F, and F stands for from, so move from. T is also present. T is the opposite of from. T stands for to. And then finally, there is UI, which stands for upper immediate. Right. So with this terminology explanation, L stands for load, S for store, M for move. B, H, and W stand for byte, half word and word, unsigned, from, to, and upper immediate. We can look at the instructions one by one. So here we are. So let's just try to understand what's up here. So using the terminology that we just saw, LB will stand for load byte. LBU would stand for load byte unsigned. LH will stand for load half, LHU for load half unsigned, LW for load word, LUI for load upper immediate, SB for store byte, SH for store half word, SW for store word, MF high will stand for move from high, and so on. MF low, move from low, move to high, and move to low. So let's just look at the example over here. So this is an instruction which is load word R2 for R3. Now we know that the load word instruction is it's a load instruction, so it is used to copy data from main memory into a register. The register is being specified in register direct addressing mode in this case. So R2 is the destination operand of this load word instruction. And I am following the convention of putting the destination operand first in this particular case. Now the rest of this instruction must let us know from where in memory, in other words the address of the memory location which is going to be copied into register R2. And as we just saw, the load and store instructions all use the base displacement addressing mode to indicate their memory operands. And what we have over here is the base displacement operand. The base register is specified as R3 and the displacement value is 4 or plus 4. So what this instruction means is, as indicated in the meaning column, the address of the operand has to be calculated as the sum of the contents of R4 plus the constant, the contents of the value R3 plus the constant 4. So once this calculation has been done, that particular word of memory can be read, and that will be the new value of the register R2, destination register. So the contents of memory address as specified by 4R3 are copied into register R2, and that's the meaning of the instruction. Similarly, if there was a load half instruction, it would load into the register R2 not 32 bits but 16 bits, because half stands for half word. And this similarly with load byte. Load byte will look like load word. It will have a destination register and it will have a memory address specified. But instead of copying 32 bits, which is what would have happened in the case of the load word instruction, the load byte instruction will cause only 8 bits to be copied. Okay, I'll make a comment about LUI a little later. Now similarly, there are the store instructions. There is store byte, store half, and store word. And as seen in this example, the example is store byte R2, -8 R4. So the store instructions in general are used to copy a value from a register into a memory location. And as can be seen in this example, the register I want to copy the byte from is R2, and the destination address in memory where the value is to be copied is specified by the base displacement addressing mode -8 R4, which is why the meaning is take the contents of the register R2 and copy them into memory location, which is calculated as the contents of R4 minus the displacement value 8. Right. Next we have the move instructions, and these move instructions are used to transfer values from or to the high and low registers. In other words, I can copy a value from register R1 into the register high using move from high R1. So using this collection of 4 instructions, I can use the high and low instructions for any purpose that I want as a programmer, because I could have values which are in registers, general purpose registers, and then transfer them to high or low using these instructions. Okay. Now finally, before moving ahead, let me just make a comment about the LUI instruction. As mentioned, the LUI instruction stands for load upper immediate, and this instruction, an example of this instruction would be something like load upper immediate. So as with any load instruction, the load upper immediate instruction is one that can be used to copy a value into a register. So it must have a register as its operand. The other operand is going to be an immediate value, and in this case the immediate value is going to be a 16-bit immediate value. For example, the immediate value might be -16, or let me just use a better example than that. What I'm going to do is, rather than specifying the example in decimal, I'll specify the example in hexadecimal. This way you'll get used to seeing hexadecimal values, and I'll use a typical hexadecimal value, let's say hexadecimal ABCD. Remember, hexadecimal base 16, therefore the digits can go beyond 9 to A, B, C, D, E, and F. So what does load upper immediate R3 ABCD do? Okay, now you have to remember that R3 is a general purpose register of the MIPS1 instruction set, and it is therefore a 32-bit register. It's of 32 bits in size. What load upper immediate does is it causes its 16-bit immediate operand to be loaded into the upper or most significant bits of the destination register. So the A, B, C, D gets loaded into the most significant 16 bits of R3, and the less significant bits get values of 0. So this is a very special kind of instruction. We'll see why this is useful again a little later in the lecture. So with this, we sort of understood the load, store, and move instructions. You'll notice that I've highlighted the LB and LBU instructions, because I haven't actually indicated what the difference between these two instructions are. So let me do that next. So LB and LBU. LB, as we understand, is load byte. LBU is load byte unsigned, and we need to clearly understand how they are different. So we know that LB can be used to transfer a byte from memory into a given register. LBU can also be used to transfer a byte from memory into a given register. How do they differ? Okay, both do the same functionality, loading a byte from memory into the least significant 8 bits of the destination register. How do they differ? They differ in how they affect the rest of the destination register. Remember that each of the MIPS1 registers is a 32-bit register. If you load a byte into the register, that tells you how 8 of the bits of the register are modified. What about the remaining 24 bits? Now, the two instructions differ in how they affect the remaining 24 bits. Let's look at two examples. On the left I have load byte R1, 0, R2. So this is some memory address and base displacement. And on the right there's load byte unsigned R1, 0, R2. So in both cases the destination register is R1. And let's just suppose that the byte which is going to be copied from memory is the byte shown in yellow down here. when I say that I am showing you the byte in yellow, I am suggesting that it could take on any value. For example, the value could be 0, 1, 1, 1, 1, 1, 1, 0. That is an 8-bit quantity. So I am just showing you a yellow example of what the byte might be. So for both load byte and for load byte unsigned, the effect of the instruction is that the byte from memory goes into the least significant 16 bits, the least significant 8 bits of the register. Remember, the register is of size 32 bits. So the byte from memory, whatever it is, occupies the least significant bits. In other words, the bits from 0 through 7, if I number the bits from right to left. The most significant bit is what I would call bit 31. So both of them do this. They load the byte into the least significant byte. The difference between the two is that load byte unsigned always fills the rest of the register with zeros, whereas load byte signed or load byte will fill the rest of the bits of the register in different ways depending on what the most significant bit of the byte which has been loaded from memory is. For example, if the most significant bit of the byte that has been loaded from memory is a 1, as shown in the example over here, then what the load byte instruction will do is it will fill the remaining 24 bits of R1 with 1s. Similarly, if the most significant bit of the byte that is loaded from memory is a 0, then this load byte instruction, this is what load byte does, this is what load byte unsigned does. What the load byte instruction would do is to fill the remaining bits of register R1, the most significant bits of register R1 with zeros. So if you think about this, what is actually happening is that in the case of load byte unsigned, regardless of what the bits that are loaded from memory are, the remaining bits are always filled with zeros. And this is what is known as zero extension. So the byte that has been loaded from memory is extended into 32 bits using zeros. Whereas in the case of the load byte instruction, the way that the remaining bits are filled or extended depends on what the most significant bit of the byte that was loaded is. Now the most significant bit, as we have seen, if we are talking about a 2's complement value, the most significant bit gives you some information about the sign of the value. If it was a 0, we know that the value, if interpreted as a signed integer, is a positive value, whereas if the most significant bit was a 1, we know that the value represents a negative value. Therefore, the operation which is done by the load byte instruction goes by the name sign extension. If the most significant bit of the byte is a 0, the rest of the register gets filled with zeros. If the most significant bit of the byte was a 1, the rest of the register gets filled with 1s. And that's the difference between the load byte and the load byte unsigned. Okay, so they have in common that they load a byte from memory into the least significant 8 bits of the destination register, but otherwise one does zero extension, the other does sign extension. Okay, now moving right ahead, we'll next look at the arithmetic and logical instructions of the MIPS1 instruction set. And in this table I'm showing you a subset of the instructions. As indicated in this comment over here at the bottom, I have left out 2 classes of instructions, the shift instructions and some comparison instructions, since if necessary I will explain them when examples which use them come up. So in this particular table, the top row has add and subtract instructions. The second row has our multiply and divide instructions, and the third row has a collection of logical instructions. And once again, before going through the instructions one by one, let me just put down any terminology which is used which might help in our reading of the table. First of all, in some of the, we've already seen that I stands for immediate, as in the case of the load upper immediate instruction of the previous table, I stood for immediate. Now in the terminology used in the meaning column over here, I have used LSW and MSW, which I would like you to read as least significant word LSW and most significant word MSW. And finally, I have used SE to stand for sign extension. In other words, the operation that we just saw that the load byte instruction does in the hardware, Sign extension is the idea that a value can be extended to more bits by just replicating the sign bit or the most significant bit for the remaining bits that have to be filled. So with these three additional pieces of notation, we can understand the contents of this table. Okay, so as we go through this table, we see that there's an add instruction. I should at this point mention that the arithmetic instructions that I'm showing you in this table relate to integers, and the MIPS instruction sets have separate instructions for real or floating point values. And again, as we come across the floating point operations in examples, I will introduce the floating point instructions. For the moment, just interpret everything that you see here as relating to integer values, not to floating point values. So there is an add instruction which can be used to add integers. Add u, which we understand stands for add unsigned, so from which we infer that add must refer to adding of signed integers. Add I, we know that I stands for immediate, so this is add immediate. Add IU, which must be add immediate unsigned, and then corresponding subtract instructions such as subtract and subtract unsigned. There's a multiply, there's a divide. Multiply u, which must be multiply unsigned. Divide u, divide unsigned. Then various logical operations, and immediate, or immediate, exclusive or immediate, nor. So a representative collection of logical instructions. If we look at the table, I give you a few examples for example, in the add and subtract line. I've given you two examples which use the add, basically the signed integer addition instructions, the add R1, R2, R3 and the add immediate R1, R2, R6. You'll recall that I mentioned that all of the arithmetic and logical instructions take operands in only two addressing modes. The two addressing modes which are used by the MIPS1 instruction set for arithmetic and logical instructions are register direct and immediate. In the register direct addressing mode, the operand comes out of a general purpose register. In the immediate addressing mode, the operand is specified inside the instruction. So we see an example of an add instruction which takes all its operands out of registers first. Add R1, R2, R3. So it takes its two source operands out of R2 and R3, does the addition using a signed integer adder, and puts the result into the destination register R1, as indicated by in the meaning on the right. There's also an add immediate instruction which can be used to add a value which you specify inside the instruction, such as 6 in the second example, to the contents of a register, with the result going into another register. So the add and add immediate instructions can be used to do addition on signed integer values, which gives you some indication that the 6 that we have over here could just as well have been a -6, and then this would have been adding -6 to R2. And that would sort of motivate the reason for not having a subtract immediate instruction. There is no need to have a subtract immediate instruction, since if there had been a subtract immediate instruction, it would have just had a positive value of 6 as the second operand, and I can achieve the same effect by having a -6 as the second operand for the add immediate instruction. So the designers will avoid having instructions which are not necessary, in the sense that if the functionality of subtract immediate can be met by the add immediate, then there's no need to include the subtract immediate instruction. It would just be a waste of the hardware, because the hardware would have to be a little bit more complicated because there's one more instruction. How does unsigned arithmetic differ from signed arithmetic? That is a more subtle question. We know that there are signed integers and there are unsigned integers, and we know that there are some situations where we use one and some situations where we use the other, and very clearly the arithmetic on the two must be mildly different. For example, it is conceivable that overflow may be an issue or a mechanism through which they differ, but there are separate instructions, meaning that there's actually separate hardware to deal with arithmetic on integers which are signed as opposed to arithmetic on integers which are unsigned. Okay, now as with the add and subtract instructions, the logical instructions have variants in which there are all operands coming out of registers and one operand coming out of a immediate value, such as shown in the or immediate example, where the value in register R2 is ORed with an immediate value, which in this case is the value f. Now, the notation which is used here tells you that since R2 is a 32-bit register, when the OR operation is done, the second operand must also be a 32-bit value, whereas the operand which has been specified over here, in actuality this is an 8-bit operand, but you know that all immediates in the MIPS1 instruction sets are 16 bits in size. So, this is actually a 16-bit value. You can think of this as being the same as 0x0f, it's as many zeros as are required to make it into a 16-bit value. So, the question is, how do you generate a 16-bit value out of the, how do you generate a 32-bit value to do the OR out of the 16-bit immediate which has been specified in the instruction? And the answer is that is done using sign extension. So, once the sign extension is done by the hardware then does the OR using a simple OR circuit, and I am using the same operator for OR that you are used to seeing from C. The C OR operator is that pipe, which is what is used in this example. And so, with this we have a somewhat of an understanding about the add, subtract and the logical operators, logical instructions. I have left the multiply and divide instructions for a separate slide because they are somewhat curious. The first thing you will notice about the multiply and divide instructions is that the multiply instruction seems to have only 2 operands. Now, we are used to seeing arithmetic instructions where there are 2 operands which are operated on using an arithmetic operator, and the result goes into a destination. So, there is the third operand, the destination operand. The multiply and divide instructions are different. They have only 2 operands. This requires separate comment. Okay, but in fact, before coming to that, I wanted to say a few words about how to use these instructions for a specific objective. The objective which I am going to target is, let us suppose that I want to get some constant value into a register. How do I do that? That is the question which we will address. So, the question of getting a constant into a register using the MIPS1 instruction set. And we will look at two separate cases. First of all, let us suppose that I want to get a 16-bit value, this specific 16-bit value, hex 01AB into register R3. Okay. So, I know that I can do this by putting the value. One way of doing this is that I could write a program where this value is declared as a constant, and I can then make that available in a memory location. I suspect that the compiler will make that available into a memory location, and then I could load that constant into the register using a load half instruction. Right? That is one way that this could be done. But the question which I want to address here is, how could I write a sequence of instructions using which I can get the 16-bit constant value? In other words, the constant value appears in one of the instructions into the register R3. Now, in order to do this, I will have to use one of the arithmetic instructions from the previous table. And there are many possible ways of doing this. I am going to suggest one in which I use the add immediate instruction. Recall that in the add immediate instruction, I can specify a 16-bit immediate value. What I have here is a situation where I want to deal with a 16-bit immediate value. Therefore, I will use the add immediate instruction to add this 16-bit immediate value to something, and then I will use R3 as the destination register. Now, since my objective is to get that 16-bit immediate value into R3 without modification, I know that the thing that I want to add it to is in fact the value 0. Where can I get the value 0 from? Fortunately, I have the value 0 always available in register R0. And therefore, with a single instruction, add immediate R3 R0 0x 01AB, I can achieve my objective. Remember that R0, in this instruction, add immediate, R3 is the destination, R0 and hex 01AB are my 2 source operands. R0 always contains the value 0. Therefore, what this instruction is doing is adding 0 to the hex value 01AB and putting this into register R3. In other words, it is putting this constant value into register R3, which is what I wanted to do. So, when you read MIPS1 programs, you will frequently find the add immediate instruction being used for a purpose like this. If you look back at the table, you notice that I could just as easily have used the AND immediate or the OR immediate, several other instructions which could have been used in slightly different ways. but this is possibly the easiest way of doing it. Okay, now that we've seen how I could get a 16-bit value into a register using the MIPS instruction set, how do I get a 32-bit value into a register in the MIPS instruction set? Okay, now 32-bit values, 32-bit constant values are always going to be a problem in the MIPS instruction set because they can never be contained inside an instruction. The most constant information that I can contain in an instruction is 16-bit signed value. Therefore, very clearly, in order to achieve this objective of example 2, I'll have to use at least 2 instructions. It will not be possible to do this with 1 instruction, unless I go through the path of using load word to load this constant, which I know is available at some particular memory location. Now, short of that, I'll have to use at least 2 instructions. And this is where the load upper immediate instruction is going to be useful. If I use a load upper immediate to get the most significant 16 bits, in other words 0, 1, A, B, into the most significant 16 bits of R4, and I recall that from my description of the load upper immediate instruction, it puts zeros into the least significant bits, then the effect of the first instruction is going to be that I have 0, 1, A, B in the most significant bits of register R4 and zeros in the less significant bits of R4. So all that remains to be done is to get C, D, E, F into the least significant bits of R4, which I can do using an add instruction. Okay, so I add to R4, which already contains in its most significant bits 0, 1, A, B. Right? So the way to look at this is, of my 32-bit register, after executing the load immediate, I have 0, 1, A, B in the most significant bits and zeros in the least significant bits. The add immediate instruction is adding C, D, E, F to this, so that the net effect is that after the add immediate instruction, I have 0, 1, A, B, C, D, E, F in the register. Now, you'll notice that I have used a add immediate, which is a signed integer addition. But I need not worry about carry in this case, because when I add C, D, E, F to 0, 0, 0, 0, there is no possibility of carry. And therefore, this 2 instruction sequence can be used to load a 32-bit value into a register. Now, this is actually a very important sequence of instructions. We're going to see this sequence of instructions very often, because we'll frequently need to get a 32-bit value into a register. And let me give you one very simple example where this may be necessary. You'll recall that all of the load and store instructions in the MIPS instruction set use the base displacement addressing mode. And in the base displacement addressing mode, there is a base register to which some displacement is added. The displacement is a signed quantity, could be positive or negative. Therefore, in order to specify the location of an operand in memory using the base displacement addressing mode, I must be able to get an address into a register. I, as a programmer or as a compiler writer, I must have a mechanism to get an address into a register. And addresses are typically 32 bits. For the moment, we'll assume that the addresses are at least 32 bits in size. So I have to have a mechanism by which I can get a 32-bit known value or constant into a register. And this is the mechanism that is going to be used in the code segments that we write to do this, which is why I talked about it this early. Okay, now with this we have seen the MIPS1 data transfer instructions, in other words the loads, the stores, and the moves. We have seen the MIPS1 arithmetic and logical instructions. We have looked at some very simple examples. After this we have to look at the MIPS1 control transfer instructions. And after that, we'll be in a position where we know the entire MIPS1 instruction set and can start looking at more and more complicated examples towards our objective of actually figuring out how we can make our programs run faster.